Greetings, class! Have you ever wondered how a massive construction crane, hovering hundreds of feet in the air, lifts literally tons of solid steel without tipping over and crashing to the ground? Or how a tiny pivot point can hold up a massive suspension bridge? It looks like magic, but it's actually a really beautiful, delicate dance of physics. Today, we will study rotational and linear equilibrium.
Now, before we start solving complex physical systems or, building any bridges ourselves, we've got to lock down our foundational definitions. First up is rotational equilibrium. This is simply a state where an object shows absolutely no tendency to change its speed of rotation. It's perfectly stable. And second, we have the principle of moments. This rule dictates that rotational stability happens if and only if the sum of the clockwise moments about any given point perfectly equals the sum of the anticlockwise moments. Keep those two ideas firmly in your mind as we go forward.
All right, let's take a quick look at our roadmap for today's explainer. We're going to start with the principle of moments, move on to complete equilibrium, explore vector representations, apply those conditions, and finally, look at some real-world uses.
Let's jump right into section 1, the principle of moments, understanding turning effects.
Okay, let's really dive into this first core concept by looking at exactly how forces cause rotation, and more importantly, how we stop them from doing it. I want you to imagine a simple seesaw battle. If you balance a meter rule horizontally on a little triangular pivot right near its center, any weight you add is going to try and turn it, right? Weights on the left push for an anti-clockwise rotation, while weights on the right push for clockwise. When you hang weights on both sides, that rule is going to do one of three things: dip right, dip left, or stay perfectly flat. And that perfectly horizontal state? That's the absolutely crucial one. It means all those turning effects are completely neutralized. And the really fun part is that you can have a super heavy weight right close to the pivot on the left and a much lighter weight really far away on the right, and they can completely cancel each other out.
These are the key points related to this topic. Focus on them carefully as they are considered essential for your exams.
So, how do we actually prove this mathematically? We don't just guess, we calculate something called the moment. This is just the product of a force and its perpendicular distance from the pivot point. The standard unit we use for this is the Newton meter. So, let's say you have a 4 Newton weight sitting 0.3 meters to the left. Well, 4 times 0.3 gives you 1.2 Newton meters anticlockwise. Now, on the right side, let's say a 3 Newton weight is sitting at 0.4 meters. That also gives you 1.2 Newton meters, just clockwise. Since 1.2 equals 1.2, the ruler doesn't spin at all. It's in perfect rotational equilibrium. This exact calculation is literally how structural engineers make sure a bridge doesn't flip over when a heavy truck drives across it.
The following are critical points regarding this heading. Please examine them closely as they are highly significant from an examination perspective.
Moving right along to section 2, conditions for complete equilibrium, achieving total balance. Stopping rotation is fantastic, right? But it's really only half the battle. We also have to prevent the object from flying away in a straight line like a rocket. To lock an object completely in place, we have to enforce our first rigid condition of complete equilibrium. Think about it. If you just balance the moments, the seesaw won't spin. But if someone comes along and pushes the whole thing up from the bottom, it'll still fly into the air. So condition 1 states that the sum of the forces in any direction, horizontal, vertical, or at some weird angle, must be precisely 0. There can be absolutely no resultant force. If something pushes left with 10 newtons, something else has to push right with exactly 10 newtons.
And that brings us to condition 2, which we've already met. The sum of moments about any point must be 0. True complete equilibrium means satisfying both condition 1 and condition 2 at the exact same time. Picture a uniform horizontal beam resting on 2 pillars. The beam's weight pushes straight down through its center, while those 2 pillars push up. For condition 1, the total upward push from the pillars has to equal the downward weight of the beam. And for condition 2, the turning effects must all cancel out. Without both of these conditions working together in perfect harmony, well, gravity is going to win.
Next up, section 3, vector triangles and polygons, graphical representations. Math is incredibly useful, obviously, but what if we could prove balance visually, just at a glance? If you're a visual learner, you're going to love this part. When we represent forces as vectors, arrows showing both direction and magnitude, we can graphically check for equilibrium. If you have 3 forces acting on an object, you just draw them tip to tail. If that object is perfectly balanced, those 3 arrows will form a perfectly closed triangle, bringing you right back to your exact starting point. It's literally a visual guarantee that the resultant force is 0. And hey, if you're drawing the forces for a real-world bridge design and that triangle doesn't close, well, that bridge is going to move, and definitely not the way you want it to. Now, what's really cool is how this exact same geometric logic scales up to much more complex systems with 4, 5, or even 50 forces. Instead of a simple triangle, you're going to end up with a closed vector polygon. Every single arrow drawn tip to tail must eventually loop perfectly back to the start. Imagine a traffic light suspended above an intersection by 2 angled cables. You've got the downward pull of gravity and 2 tension forces pulling up and sideways along the cables. Draw them tip to tail, and they snap together into a closed shape. The upward parts of the cable tension perfectly fight gravity, and the sideways pulls from the cables perfectly cancel each other out.
Moving forward to Section 4, applying both conditions, solving complex problems. Okay, let's put our equations to the test with a classic standard A-level worked example. We're going to break down a typical beam problem. Imagine a 6-Newton uniform beam, 2 meters long, resting on 2 supports, 1 at each end. Let's call them R1 and R2. Now plop a heavy 10-Newton load near the left side, just 0.5 meters from support R1. Our job is to find the reaction forces at both of those supports. Step 1 is a really clever trick. We're going to take the moments about the left support itself. Why do we do that? Well, because the distance of the left support from itself is 0. This instantly eliminates one unknown from our math. So we add our clockwise moments. That's the 10-Newton load plus the beam's own weight, which totals 11 Newton meters. We set that equal to the anticlockwise moment of the right support, which is the unknown force, R2, times its distance of 2 meters. So R2 times 2 equals 11. Simple division tells us R2 has to be exactly 5.5 newtons.
Once we've got one side figured out, the rest is honestly a breeze. We just apply condition 1, linear balance. Our upward forces absolutely must equal our downward forces. The total weight pushing down is the 10-Newton load plus the 6-Newton beam, giving us 16 newtons total. Therefore, the 2 pillars pushing up have to combine to equal 16 newtons as well. Since we just figured out the right pillar is pushing up with 5.5 newtons, we just subtract that from 16. That means the left pillar R1 has to be pushing up with 10.5 newtons. This exact 2-step method, using moments first to find one unknown and then forces to find the other, is basically the gold standard for almost every equilibrium problem you're ever going to face.
Which leads us beautifully into Section 5, Real-World Applications, Equilibrium in Action.
Let's step out of the textbook for a minute and see how these rigid mathematical laws govern the physical universe all around us. Right now, if you just hold your phone steady in your hand, your forearm is acting as a biological lever. Your elbow is the pivot point, the phone is the load causing a moment, and your bicep muscle is pulling up to create the exact opposite moment to achieve rotational equilibrium. Pretty cool, right? Out in the city, those giant tower cranes use massive concrete counterweights on their short back ends to perfectly balance the enormous clockwise moments of steel beams hanging off their long front ends. And even at 30,000 feet, aircraft wings are positioned so meticulously that the upward lift force perfectly balances the plane's weight without causing any net turning effect, because, a spinning commercial airliner is generally considered a pretty bad thing.
Okay, let's rapidly review the high-yield technical takeaways from today's explainer to lock these concepts permanently into your memory. Remember, complete equilibrium means an object is completely dead in the water, absolutely no linear acceleration and no rotational acceleration. You achieve this total balance by ensuring all upward, downward, left, and right forces cancel each other out, and that all clockwise and anti-clockwise moments cancel out using force times distance. Whether you're sketching out closed vector triangles on a napkin or solving complex 2-step equations, these physical laws remain totally unbreakable.
Before we wrap up, I'm going to leave you with a final real-world puzzle to test what we've just covered. If a commercial aircraft's center of mass suddenly shifted backward mid-flight due to cargo movement, how exactly would the required balancing moments and aerodynamic lift forces need to change to maintain both linear and rotational complete equilibrium? How does the pilot, or the physics of the plane itself, compensate to prevent a disaster? Think about that carefully as you review your notes. Thank you so much for joining me in this explainer, and keep exploring the incredible balance of our world.
The screen presents essential keywords for this topic categorized by different exam boards. These terms need careful focus while studying as they are very important and should not be ignored at any cost. Moreover, past paper analysis for each board and paper type is also included. Pay close attention to this section as it will significantly strengthen your preparations. Also make an effort to understand how each keyword is used in the context instead of just memorizing them separately. Regular use of these terms in past paper practice will improve your accuracy and exam performance.
Please subscribe our channel to get more educational videos. Thank you.